This is a short recording of a lecture and solving some problems for complex numbers, and I put a motivation here. So, for example, the Schrödinger equation used all over in quantum mechanics heavily relies on complex numbers. You see the I right here, and then the solution of the wave function incorporates complex numbers. Respectively, for polynomials, we're always looking for zeros for polynomials, and a polynomial of 8th degree has 8 roots, and some of them are real numbers, but the other ones are complex numbers. In AC circuits, if you look at in electronics books on AC circuits, you will see complex numbers almost every other page. There's just no way around it. Some integrals in calculus cannot be readily integrated, or some functions cannot be readily integrated using real numbers, so there's a switch to complex numbers, and then with those some functions can be integrated with complex numbers. Okay, let's look at some definitions from the book, and I pretty much just copied these here. So a definition is that a complex number z equals a plus bi, with the I being the square root of negative 1, and these are the two parts. This is the real part, this is the imaginary part. The two cannot be combined, and then it's obvious that when you square I, you come up with negative 1 as you square the square root of negative 1. Another definition to complex numbers: z1 and z2 are added by combining their real parts and separately their imaginary parts. To complex numbers, z1 and z2 are multiplied using the distributive law. So pretty much what you do is you do a1 times a2, that would be the first part, and the last part would be that b1 times b2, and because of the I times I here, you get an I squared, which is simply a negative, and therefore that last part in the FOIL method becomes real as well, with a negative in front of it, and perhaps the b1 or b2 are negatives as well, so that sign may change. And then do the outer and the inner ones, where you have the imaginary parts now, a1 times b2 I, and b1 times a2 times I. And then again you get real and imaginary parts. Division of complex numbers as such is not possible. Instead, what you do is you multiply both the numerator and the denominator with the complex conjugate of the denominator. So z equals a plus bi, the complex conjugate to that is z prime or z star equals a minus bi. If you use the FOIL method on these two numbers, as you multiply them, you will see that the outer and inner parts cancel out. They become 0, therefore there is no imaginary part, and you're pretty much left with a squared plus b squared. I say in here it looks like the difference of squares, or similar to a difference of squares when you multiply these two numbers, but obviously there's a plus in the middle, and that is because when you multiply this with this, yes, you do get a negative, but with the I squared you get another negative, and that turns then to that positive here. The result is a real number. And then writing it as a fraction here becomes rather complicated. These two are complex numbers, these two are complex numbers. Multiply with the complex conjugate here, and you come up with a complex number in the numerator. In the denominator, because it's the complex conjugate of that original complex number, you come up with a real number in the denominator, and therefore the quotient is a complex number itself. Alright, some problems. I already worked these out, so I'm just going to glance over them here as I go through. So I expect not to do any algebra steps because it's already all worked out. Square root of negative 121, we'll take the square root of 121, which is 11, and leave the remaining square root of negative 1 as I. Square root of negative 400, square root of 400 is 20, leave the square root of negative 1 as I. Here, we really cannot take the square root of 18, so I'm just going to leave it as square root 18 times I. You could perhaps take the 18 apart into 9 times 2 and then write this as 3 times the square root of 2 times I. Okay, and this other one here, square root of 45 would be the same as square root of 9 times 5, so alternatively this could be written as 3 times the square root of 5 I, 3 times because you take the square root of 9, which is 3. Alright, let's see. Find all x and y such that both of them are between 0 and 2 pi. So cosine x plus I sine y equals sine x plus I. You have to separate them into the real part. So cosine x equals sine x, and separately from that, I sine y equals I. So cosine x equals sine x. The only way that works is at an angle of 45 degrees, which is in the first quadrant. So pi over 4 is one of the solutions. There's a second one that is at 225 degrees in the third quadrant, where both of them come out negative. So 5 over 4 pi works as well, 225 degrees. And for the other one, where it says I sine y equals I times 1, just to point that out, therefore sine y must be 1, and that happens only at 90 degrees, so y equals pi over 2. Okay, a little bit harder here. This entire expression, again, the real part, sine x squared plus 1 has to equal 2 cosine x, and here it is. Use the Pythagorean so that I deal only with one trig function in order to solve that. So I have the cosine squared and the cosine. Rearrange, looks like a binomial, a quadratic equation that I try to solve, and I can actually do that with factoring. If I look at this one here closely enough, I can see that that's what I get. Cosine x minus 1 gives me, cosine x minus 1 means that if that has to be 0, then cosine x equals 1, and that only happens at x equals 0. The other parentheses here is not possible because it would say cosine x equals negative 2, and the cosine x cannot go beyond 1 or negative 1. So this particular parentheses doesn't yield any solution. I tangent y equals negative I pretty much boils down to tangent y equals negative 1. So I guess I could put a 1 right here. There. So tangent y equals negative 1, and that happens at an angle of 45 degrees, except it would be a positive 1, so therefore it's 135 degrees in the second quadrant, 3/4 pi, and again in the fourth quadrant at 315 degrees, so 7/4 pi. That's where the tangent of 315 degrees comes out to negative 1. Alright, combine the following complex numbers. This is the addition and subtraction of complex numbers. So again, real parts separately from imaginary parts. So 7 plus 3 is 10. 2i minus 4i is minus 2i. And you can see it over here too. 3 plus 2, negative 5i plus 4i. 5 minus 3, 2i minus 6i, and there it is. I don't think I have to say that out loud. 6 minus 4, 7i minus 1i, and there you go. Okay. Simplify each power of I. I to the first power is simply I squared, as I squared the square root of negative 1, I come up with negative 1. Then I cubed, well, that's I squared times I. So negative 1 times I is negative I. And I to the fourth power, well, that's I squared again. So negative 1 times negative 1 is 1. And then at I to the fifth power, it would start over here. Because now it would be I to the fourth times another I, which comes out to I. And then I to the sixth would be this, I to the seventh would be this, I to the eighth would be that. And then at I to the ninth, it starts over again. So it's recurring every fourth power. So that means that I to the 12 is the same as I to the fourth. So 4, 8, 12 yield the same, 1. I to the 13 is the same as this one over here, because I to the 12 again is just 1 every 4 powers. 4, 8, 12, 16, 20, you come up with 1. So you just subtract a 12 from that and you end up with I to the first power, which is I. Subtract 12 from the 15, that's I to the third, and you come up with negative I. I to the 14th, subtract 12, you come up with I squared, which is negative 1. Again, the reason why I subtract a multiple of 4, in this case 12, is that I know that every 4 powers, I to the 4th, to the 8th, to the 12th, to the 16th, to the 20th, to the 24th, I come up with 1, and therefore I just need to count up from that 12 and see what happens with I squared in this case. This one here, subtract 32, so I squared is again minus 1. This one here is the same as I to the 4th, so just 1, or I to the 0 is also 1. I to the 33, subtract 32, so I to the first is simply I. Subtract 32, so I cubed is negative I. That might have been just a little bit out of screen. Okay. Alright, find the following products. So here's where the FOIL method comes in. So 2 times 3 is 6. Then I'm going to do the last, which is plus 4i times negative I. So that comes out to negative 4i squared. And then I do the imaginary parts, the outer and the inner. So I apologize for this little box always showing up. 2 times negative I and 4i times 3. So here they are, the two imaginary parts. Negative 2i plus 12i is 10i. And the real parts is 6 minus 4i squared. That I squared is a negative 1. So this turns out to be 6 plus 4 equals 10. 3 minus 2i squared, well, that's square the 9. Square the last one, negative 2i squared is a positive 4i squared. When I resolve the I squared into a negative 1, that one here becomes a negative again, so 9 minus 4 equals 5. And then I have the outer and the inner parts are both 3 times negative 2i, so I have negative 6i, the outer part, negative 6i, the inner part, which comes out to negative 12i. Okay, this one here, that one here actually is the complex conjugate of this one here. Notice the numbers are the same except there is a negative. That makes it the complex conjugate. And so here we expect a real number to come out with the imaginary parts canceling. So 4 times 4 is 16, plus 5i times negative 5i is negative 25i squared. And now what I could do is I could write here, let's see, plus, actually minus 4 times negative 5i, so minus 20i, and then plus 5i times 4 equals 20i, and that of course cancels out, so the imaginary part is 0, and it's 16 plus 25. Again, the plus is because of that I squared here turns that sign around. So 16 plus 25 is 41, which is a real number. Okay, find the following. So this is subtraction. 3 plus 2i divided by 3 minus 2i. It looks ugly. Notice that the calculation isn't that easy as it was before. So in order to divide these two and come up again with a nicer looking complex number, I multiply both the numerator and the denominator with the complex conjugate. Complex conjugate of this one here, right here, is 3 plus 2i. So there it is. And I multiply both numerator and denominator with that. In the denominator here, I just expect to get a real number, which is going to be 3 squared is 9, and then 2 squared is 4 with the I squared attached to it, minus that minus here with the, because of the I squared becomes a plus, so 9 plus 4 equals 13. There is that real denominator. And then as you calculate through the denominator here, you come up with this one here, 9 plus 4i squared, 6i. Combine 9 minus 4 right here is 5. And again, you should see that the I squared here introduces a negative right there. And then 6i plus 6i is 12. And separating those two parts, here's the real part of the new complex number after the division. And here's the imaginary part after the division. Okay, and then really similar here, 5 minus 6i is the denominator, multiply with the complex conjugate right here. That yields 25 minus 36i squared. And then again, it's the I squared that turns the negative into positive, so 25 plus 36 is 61. And the numerator, it's going to be 2 times 5 is 10. I times 6i is 6i squared. 2 times 6i is 12i. I times 5 is 5i. Combine these two here, that's 17i. Combine these two here is 4, because that I squared, being a negative 1, says then 10 minus 6, and that equals 4, and then split it up. Real part 4 over 61, imaginary part 17 over 61.